Welcome, let's continue our look at electrochemical cells. Today's lesson, looking at measuring standard electrode potentials. We're going to understand how to measure the standard electrode potential of a half cell relative to the standard hydrogen electrode. Last time we were talking about electrochemical cells, specifically the galvanic cell, where if you've got two half cells, one of them is going to be able to be more easily reduced, one of them is going to be able to be more easily oxidized. That's going to drive a redox reaction that's going to generate electricity from chemical energy. So essentially, these are batteries. This is what we're talking about. When you've got your batteries, you've got chemical energy stored in these batteries, and then they can drive that redox reaction with the two half cells, and that's going to generate the electricity you need to power all your gizmos and gadgets. What we're looking at today is we're looking at how we can put some numbers to this. We were talking just conceptually last time, but we can get some numbers that will really concretely tell us what's going to undergo the redox reaction, what's going to undergo the reduction reaction, and what's going to undergo the oxidation reaction. So we're talking about this idea of redox equilibrium, very in depth last time. Go back there if you need. Of half cells creates a potential difference, sort of voltage, essentially electrical energy. But we can't measure this directly for one half cell because a redox needs both processes to happen. So we can't get these absolute values, but we can compare everything against an agreed upon standard. And we can use this standard to obtain usable values. And the standard we're going to be looking at is what's called the standard hydrogen electrode. That looks like this over here. Similarities to the kinds of half cells we were looking at last time, but clearly some differences as well. So let's investigate those. The standard hydrogen electrode, called the SHE for short as the acronym. It's a redox equilibrium with hydrogen. Who would have guessed that from the name? Where we've got our hydrogen ions gaining electrons and forming hydrogen molecules if we're looking in the forward reduction reaction direction, or the hydrogen molecules losing electrons to form the hydrogen ions in the oxidation direction, or we can just write this with just a single hydrogen ion like so. So straight away, we've been looking at metals and metal ion systems last time. This is now a non-metal and a non-metal ion system. So straight away, there's going to be differences. The metallic bonding model in metals are really good conductors of electricities. We have a molecule here. We have molecular hydrogen, which is not. Our molecules are not good conductors of electricity. So there's a few differences that we have to include in our SHE to be able to complete this half cell. What else is going on? We've got gases. We're dealing with gases. So again, there's going to be differences occurring there. This is given a standard electrode reduction potential of 0 volts. So our symbol for the reduction potential, the plimsoll, saying we're at standard conditions. We'll talk about that just in a second. But we're given this as 0 volts. So this is our reference point. Totally arbitrary value. They've just decided that if we call this one the reduction potential of 0, we can only measure the cell potential when we've got both the reduction and the oxidation occurring. So let's make this 0 and we can measure everything relative to that. Thus, it being the standard. All other standard electrode potential values, reduction potentials, I'm going to use those terms very interchangeably. Mostly I'll be referring to them as reduction potentials, measured relative to this. So the more positive the reduction value that we have, the more the reduction reaction is favored, and the vice versa. So we end up with a reduction potential of a certain value in volts. The more positive it is, the more it's implying that the cell that we've attached to the standard hydrogen electrode wants to be reduced. The more negative that value is, the more the cell that we've connected to the standard hydrogen electrode wants to be oxidized. Half cells are in redox equilibrium. So we know that there are certain factors that affect equilibrium: concentration, temperature, and pressure. So if we're going to be changing these variables, we're going to be changing the position of equilibrium. So these need to be constant to make sure that all our comparisons are fair, because changing the position of equilibrium is going to change the potential value. It's going to change the reduction potential value. Sorry, is what I'm trying to say. If we change that position of equilibrium. So these need to be standard, else the voltage generated would be different, and we would end up with some rubbish results when comparing everything. Standard conditions is something we've looked at before. They're the same here. We're given a temperature of 298 Kelvin. So that's going to affect what state our substances are in. We're going to look at systems where we've got gases, systems where we've got aqueous, systems where we've got liquids, so on and so forth. So we've got standard conditions 298 Kelvin. We're dealing with solutions. So we're given that just 1 mole per decimeter cubed as the standard concentration. So we're dealing with aqueous hydrogen ions, and when we're dealing with our aqueous metal ions, we're dealing at standard conditions, so 1 mole per decimeter cubed. We're dealing with gases, so we need a standard pressure, because again, pressure can change the position of equilibrium. So 1 atmosphere, 101 kilopascals, standard pressure when dealing with our gases there. And then all our reduction potentials are measured relative to the standard hydrogen electrode, where the standard hydrogen electrode is given the arbitrary electrode potential of 0 volts. So let's look at how we can connect these up in our galvanic cells. So this will give us a standard electrode potential that we can measure. Here's the definition. Standard electrode potential is a half-cell's electrode potential measured relative to the standard hydrogen electrode. Let's have a look at this cell on the right-hand side, which is our She over here. Now, I was just saying that nonmetals cannot conduct electricity. We need to conduct electricity in our galvanic cells. I mean, that's the very point of them, to transfer electrons. So what we have is we use a inert electrode because we need to be able to conduct the current, but we do not want this to interfere in our redox reaction. So that's what we have here. We have a platinum electrode, which is able to carry the current, but will be inert. When we're talking about these standard electrode potentials, we're always talking in terms of the reduction reaction. So whenever I'm writing these redox equilibriums, I'm always writing the forward reaction as the reduction reaction. So that's why I'm also going to refer to them as reduction potentials. So just be aware of that. What else to mention about our standard hydrogen electrode? We have a gas. So we've got to make sure the gas can interface with the equilibrium down here. If our equilibrium, I might write this up here. If our equilibrium is like this, half H2 gas, these two species need to be able to interact with one another. So we have these little tubes that can trap the gas, and where this equilibrium reaction is going to occur, whether it's the reduction, whether it's the oxidation, it's going to occur at the surface of our platinum electrode here. So the platinum electrode, or whatever our inert electrode is, needs to be interfacing with both forms of our species there. So you can see it's half submerged to allow the redox reaction to occur, to either undergo oxidation or undergo reduction and have the electrons transferred to it. 3 main types of half cells whose reduction potential value can be obtained when connected to a standard hydrogen electrode. And we'll look at each of these in depth. We have the metal ion half cell, that's what we've been looking at already. The non-metal ion half cell, of which the standard hydrogen electrode is an example, and then a iron half cell. So let's look at each of these in a bit of depth here. Let's start with the ones that we're familiar with. This is what we were looking at as our examples in the previous lessons, where we've got a metal ion half cell. So we've got the half cell with the metal rod and the metal ions in solution. Let's consider 2 of them. One with a metal that's more reactive than hydrogen, and the other with a metal that is less reactive, because this is going to dictate which one undergoes reduction and which one undergoes oxidation. So let's have a look at connecting our copper half cell. So we've got the copper metal and the copper ion, and let's attach that to our standard hydrogen electrode. Remember all our little species that we got in there, all our little features. We've got the salt bridge to help maintain the neutrality of these solutions. We have our voltmeter so that we can actually get some values here. Copper is very much less reactive than hydrogen. Talking in terms of that reactivity series, copper is below that. So what this is telling us is that copper is less reactive than hydrogen. Let's recall that our metals react by losing electrons. That's how metals react. So if our copper is less reactive than hydrogen, the copper is not going to want to react because the hydrogen is there, which can. Another way to think about this is that copper's much less reactive, so copper wants to stay in that atomic metallic form. Again, it doesn't want to lose those electrons. So what this means is that copper is easier to reduce than the hydrogen system that we have here. So that means that our copper is going to undergo the reduction reaction. So we're going to have the reduction over here. That means that we have a cathode. That means that this is the negative charged electrode for all those reasons we discussed in the previous lesson. That means that in this instance, our hydrogen's going to undergo the oxidation. So we're going to have the anode, and this is, sorry, I've said negative cathode, positive cathode. And this is going to be our negative electrode over there. So that means that our hydrogen is undergoing the oxidation reaction. Our electrons are flowing this way. And what we observe on our voltmeter is we observe obtaining a positive reduction potential. So if we have a positive reduction in potential, that implies that the reduction reaction is the more favorable. And the more positive that is, the more favorable it becomes. So let's have a look at that. We have the oxidation occurring because the reduction potential of the hydrogen is more negative than our half cell we've connected it to. So we have the oxidation occurring there. We have the cathode, which is the reduction. We have the flow of electrons in that direction, which gives us a positive value on our voltmeter. Excellent. What else to say here? Just note the standard conditions. We discussed all the standard conditions for our She just before. Standard conditions, the only one we really got to worry about over here is our concentration for our copper solution. All right, let's consider the inverse of that situation. Let's consider when we have a more reactive metal, such as zinc. Using these two examples because this is what we looked at. The copper and zinc were examples we used last time. So zinc is more reactive than hydrogen. It's above hydrogen on the reactivity series. So what does that imply? That implies that zinc wants to react. It wants to lose those electrons. So the zinc is harder to reduce, which is the converse for all the inverse reasons that we discussed last time. So that means that the zinc wants to be in the ionic form. It's more reactive than hydrogen. So the zinc reacts by losing the electrons. So that one there is very much going to favor the oxidation reaction, whereas in this instance, with the hydrogen being less reactive, that very much wants to do the reduction reaction. And that's what we observe with our reduction potentials. The more positive, which in this case is our hydrogen, which is 0, that's more positive than a negative value that we get for the zinc's reduction potential. So the more positive one is the one that's going to be reduced. So let's consider what that looks like over here. In this instance, we've said that the zinc is going to want to undergo oxidation because it's more reactive. So we have the anode over there, whereas we have the cathode over here, which is going to be the reduction reaction. Our electrons are going to flow in the opposite direction. Thus, we have the opposite sign from that, implying that it wants to undergo oxidation. So the more positive the reduction potential, the more it wants to be reduced, the more it wants to stay in its reduced form, let's say that. The more negative, the more it wants to be oxidized. So we're getting all of these values by just assigning this She as a reduction potential of 0. And what we'll start doing in the next lesson is we'll start connecting half cells, not to the standard hydrogen electrode, but to other half cells. All right, so let's have a look at when we've got non-metal ion half cells. So non-metal half cells, such as the She that we've been looking at a little bit, they require an inert electrode to carry the current because non-metals cannot conduct electricity. The redox equilibrium occurs at the surface of the electrode, so it needs to be in contact, there should be a space there, with both the element and the ion. So all those reasons we were discussing just before, it's got to be in contact with the element, which in this example we've got fluorine, and the ion, and the redox equilibrium is occurring at the surface of this inert electrode, which can conduct the electrons whichever way they need to go. All right, here we go. Here's a question if you want to pause and have a bit of a go. Copy our galvanic cell here, which is our non-metal ion half cell, and see if you can annotate with the following based on the reduction potentials I've given you. Which is the anode, which is the cathode? What does the charge of each electrode have? Show the flow of electrons using our reduction potentials down here, considering what we just said about the size of the reduction potential. And then let's have a talk about it right now. All right, looks something like this. So the more positive the reduction potential, that implies the more the forward reaction is preferred. And we have a very, very, very positive value here for fluorine. That one there, which is plus 2.87. So this is telling us that this is very much going to be the reduction reaction, an oil rig cat. Always true, the little mantra we say so much in this unit. Reduction always occurs at the cathode. So that one there is going to be a cathode, and the charge of the cathode is positive in a galvanic cell, different to the electrolytic cell, all those reasons we talked about in the previous lesson. The hydrogen, the standard hydrogen electrode with its assigned value of 0, in this instance, this is more negative. So that's very much going to be favoring the oxidation reaction at the anode. So this is where we have the loss of electrons here. They're going to flow this way, which gives us that positive value for the fluorine on that standard hydrogen electrode. So this is saying that the fluorine molecules are easier to reduce than the hydrogen ions because we got that more positive reduction potential. So we gain the electrons from the standard hydrogen electrode, and we can assign that a reduction potential of plus 2.87, just obtaining these values experimentally. Same principle. The only difference is we don't have a metal ion half cell. We've got two non-metal half cells. So we just need to know how to represent that, which we represent that like this. Whenever you're drawing these, always use a ruler. Very important. Give yourself lots of space. No point cramming it into a small little corner where you can't make out all the important details. And you want to annotate everything. So you want to show what your species are. You want to show all of those standard conditions that are really important for that equilibrium position remaining constant and standard. The last kind, which is a ion-ion half cell. So we can also have half cells that contain two ions of the same element in a different oxidation state. For example, Fe3 plus and Fe2 plus. There's still a transfer of electrons occurring there. Consists of aqueous solutions, again, our standard conditions. So we have those standard concentrations, 1 mole per decimeter cubed, and we have those inert electrodes because they're going to be able to carry that current, carry that electron flow without interfering in the redox itself. So look, here's another one that, some reactions can also have several ionic species. So if it's important for the redox, you've got to include it in your half reaction. But look, let's just not look at that right now. Let's just have a look at the differences that we have here. So our standard hydrogen electrode on the right-hand side remaining exactly the same. Our ion-ion half cell, we've got the two ions in the solution there. Platinum electrode again to be able to conduct that current, and we can just submerge that in there. Again, it's all going to be occurring on the surface of that electrode. But yes, there's no point having it out of the electrode because all of our important species are in the solution. So just a slightly different way of drawing, but the exact same type of question. Can you copy and draw, mark the anode, the cathode, the charge of each electrode, the flow of electrons using our electrode potentials down there? Consider what we've said about the sign of the reduction potential, what that means for the reduction, what that means for the equilibrium. I'll give you the answer here now. So it's going to look not dissimilar to our previous one because again, our reduction potential there is more positive than the standard hydrogen electrode. So we got the more positive, so we're very much favoring the reduction reaction here. So that means this is our reduction, therefore it's our cathode, therefore it's our positively charged electrode in the galvanic cell. Our more negative reduction potential, our She with the 0 volts here, that's very much going to be our oxidation reaction at the anode, which is negative. Oxidation is loss of electrons, so our electrons are lost here and they flow in that direction, and thus we end up with the reduction potential as a positive value for that one there. Now, you're of course not going to be expected to memorize these reduction potentials. That would be an absolute exercise in futility. There's all these have been measured and tabulated as I pad out whilst I'm opening up this over here. So, you know, you can get these in tables. You can look them up online, probably given to you in an exam question. And you can see that we've got a whole bunch of redox equilibriums. We've got a whole bunch of different values differing in magnitude. Some are positive, some are negative, but that's all giving implication about its reactivity, essentially. Does it want to be reduced or does it want to be oxidized? And we've got Old Faithful in the middle here, which is our standard hydrogen electrode. So where we're going to go from here is we're going to start looking at connecting these, you know, two of these half cells, and what does that mean for our galvanic cell, and what does that mean for how much electrical energy is produced. But look, that's all on the next one. What have we done today? We described the standard hydrogen electrode, and we have described methods to use to measure the standard electrode potential of metal or non-metals in contact with their ions in aqueous state, and ions of the same element in different oxidation states. Task as always, if you want a little bit of consolidation, you want to practice, you can pause there, work through those, and that concludes our look at measuring standard electrode potentials. Look forward to next time where we'll keep looking at these galvanic cells. Have a good one. See you later.